talking to you about running Linux on mobile devices and how it involves a different approach to embedded software than the one we usually know. So I'll start with a brief introduction of what I mean about mobile devices. Then I talk about the build system and distribution model we use in this community. I'll go back into more details about the boot process, hardware support and device drivers, and finally a word about the system architecture and some of the specific issues we're facing on such devices. And finally, I'll talk briefly about the special case of Android devices, because as you probably know, Android is based on the Linux kernel, so there are some of those devices which can run a kind of normal Linux system. But first, a few words about myself. I'm a senior software engineer working for Collabora. My line of work consists mainly of creating and maintaining custom distributions for embedded systems based on either Yocto or Debian. I've been a free software enthusiast for more than 20 years. And currently I'm a Debian maintainer and also the founder of the Mobian project, which is a Debian derivative targeting mobile devices. So basically, what are exactly mobile devices? In a sense, they're basically portable computing devices, usually based on a system on chip with ARM cores. These devices don't rely on a permanent and always available external power source. They also include a display with touch input capabilities and a few expansion ports, such as a micro SD slot and USB port. And of course, and this is especially important for mobile phones, they obviously have audio input and output ports. So here are a few examples of Linux first mobile devices, which will be the main focus of this talk. On the left, on the up, you see the Pine64 Pine Tab, which is a tablet. Below is the Pine64 Pine Phone or the Pine Phone Pro, because they have exactly the same form factor. And finally, on the right is the Purism Librem 5. Those are all devices designed to run Linux operating systems as opposed to iOS or Android. And they use different system on chips. For example, the Pine Phone uses Nullwinner A64, just like the Pine Tab, but the Pine Phone Pro has the ROG chip RK3399. And the Librem 5 is based on the NXP system on chip, which is the IMX8M Quad. So what is really specific about those devices? Well, first, compared to personal computers, the mobile devices have no input method other than touch input. So that requires a few adaptations of the application design to make sure everything can work at the touch of a finger. The display is quite small as well. On mobile phones, it's typically 5 to 6 inches. On tablets, you can get 8, 10, or 12 inches displays. But yeah, that's really small when compared to laptops or even more desktop computers. And in general, such devices have a different processor architecture because they're ARM-based and personal computers are generally x86 processors. When compared to industrial embedded systems, and I'll use that word to refer to basically every embedded system which is quite specialized or single purpose, be it in the automotive industry, aeronautics, industrial process management, or even connected things. So compared to those systems, mobile devices are really general purpose devices They're meant for user interaction, and by that I mean that the user really defines how the device is used, and they're battery powered. Most embedded systems we usually work with are always connected to mains power or are part of a bigger system handling all the power needs of the embedded device. But that's not something we have in mobile devices, and the device provides its own power and mustn't rely on any external power source. So what about the build systems and distribution model used in this community? First, a few reminders about the build systems which are the most widely used in the embedded software world. First, there is Buildroot, which is quite lightweight. It creates custom firmwares and generates lightweight images you can flash on your device. It provides a limited set of third-party software also. And it basically relies on the host computer's tool chain and really builds the bare minimum for your system to work. On the other hand, there's Yocto, which is kind of the industry standard right now. It's used to create custom distributions and so has much more advanced features. It has package management built in and basically always enabled. It can be extended through external layers. So if you want third-party software, you can import meta layers such as MetaGNOME, MetaFree Desktop, MetaQt. You can also import vendor BSP layers for hardware support. And so Yocto is very flexible, but at the same time, it's quite heavy in the sense that it recompiles pretty much everything from the cross compiler to all the applications running on the device. But on mobile devices, we have a different set of expectations. First, our users want a simple installation process, as simple as writing an image file to an SD card, for example. They want to have a large choice of third-party software, which implies having a public repository with binary packages. And of course, they need continuous over-the-air updates so that they get the latest security fixes. And also, as the ecosystem is moving fast, they want to keep up with the latest versions of the mobile software. One important thing for mobile devices when compared to more traditional embedded systems is that the user is fully in control. We have an unlocked bootloader and try to avoid setting secure boot as much as possible. We want to make root access on those devices quite easy and not relying on any special hack or security exploits to get there. Also, the user must be in choice of every software he runs, be it the distribution, the graphical environment, or the applications. And obviously, we want the configuration to be fully editable. For example, a user might not want to use their mobile phone as a phone, but rather hook it into the network and make it a web server or maybe a build server or CI runner. Or you can also have more specific applications such as software-defined radio by just plugging a radio receiver to it. So we don't want to lock the user out and allow them to just do whatever they want with their devices. In order to achieve that, we're getting to more traditional distributions, and actually the current distributions available for mobile devices are all based on existing general purpose distributions. There are mobile versions of Debian, Fedora, Arch, or Alpine Linux, for example. The base distributions provides the core infrastructure, and that pretty much defines the way packages are built. In some cases, it can also provide directly the build servers we will use. for our mobile version. We have a package repository with regular security updates. And for example, Debian already has more than 30,000 packages. So that's software we don't have to carry about and just you know, pick the software from the Debian repositories, and we know it will be good quality and have security updates throughout their lifetimes. Finally, relying on a distribution which provides existing multi-architecture support is obviously a plus for us, because all packages are usually already available for ARM v7, ARM v8, and in some cases, for example, Debian, you can even have packages for ARM v6. This is not a groundbreaking idea, because there are already general purpose distributions, or at least distributions derived from general purpose ones, targeting embedded systems. One good example of that is Arnaud, a Debian derivative targeting embedded devices for the automotive, industrial, and IoT industries. However, it requires quite a bit of involvement, and the way we do things in the mobile world, being quite a small community, is a bit different. In the case of Mobian, which is the project I maintain, instead of having our own full infrastructure, rebuilding all packages from Debian the way Arnaud does, we only provide a really small overlay on top of Debian, which is about 60 source packages, which are maintained directly in Mobian, when compared to the 30,000 packages in Debian. It's really a very small number. And a significant portion of those packages are actually aimed at hardware support directly. And we don't maintain much end-user applications ourselves, but rather do all this work directly in Debian. It's heavily based on GitLab CI. Debian has its own GitLab instance, which is called Salsa, and they have a team maintaining a template pipeline for CI, allowing projects to build Debian packages and run a few sanity check and tests on those. So for Mobian, we just import this pipeline and customize it a bit with the with the CI variables, so we can get whatever we want. For example, by default, all CI runs generate both an AMD64 and an ARM64 package. We can then directly install on the device and test to check whether everything works fine. It also allowed us to implement automatic build and deployment of packages when we push specific tags. So it takes a different kind of branch in our CI pipeline and builds it in release mode, and then pushes the packages to our binary repository, so they are immediately available to everyone. And finally, the images we provide are built on CI as well. We use Devos for that, which is an amazing tool allowing you to easily create a custom Debian-based image. So you can define whatever packages you want on the image, make a few customizations, generate the image file and partition it, and then deploy the file system on it, install the bootloader, kernel, and everything. And you just have a ready-to-flash image. It's very easy to use by using just a few recipe files in YAML format. And it's quite flexible, allowing us to have some generic templates and have things take different routes depending on the device we build the image for. So let's get into more specific technical details. One of the major pain points with mobile devices and with embedded devices actually in general is the boot process. As a quick reminder, on a computer, on an x86 computer, the first piece of software being executed is the BIOS or UEFI firmware. It performs basic hardware initialization involving most devices. That includes the memory, the display, which is initialized in limited mode, of course, storage devices as well, and input devices, and even the network, if the user wants to. This firmware then loads the actual bootloader, which is located on one of the storage devices, which doesn't have much work to do. It only has to locate the kernel by using functions and primitives provided by the firmware itself. So it doesn't need to have extensive knowledge of the hardware. And then it passes control on over to the kernel, which then performs a full hardware initialization. For example, in the display, the kernel will initialize the GPU for 3D rendering and initialize all the available modes of the GPU, so you can have a high resolution display. And it, of course, starts the first user space process, PID1, which is init in the Linux world. On ARM devices and mobile devices, obviously, the process is quite a bit different. The first part is handled by the boot ROM, which is physically hard-coded into the system on chip used on the device. And this boot ROM provides an extremely basic hardware initialization. It only initializes basically the processor and main storage devices, but all the rest is pretty much left untouched. Then the bootloader kicks in, and it will be its job to perform more thorough hardware initialization. It will have to initialize the communication bus, such as I2C or SPI. It will need to initialize the main memory and probably other devices as well. And due to the architecture of system on chips, at least ARM-based ones, it's usually split in two stages. The first stage is a really small binary, which is meant to initialize the DDR memory and load the next bootloader stage. The reason for that is that ARM-based processors usually embed a really tiny amount of static RAM, a few tens of kilobytes, and this space is really not enough to run a full-featured bootloader. So we have to create first a really small binary, which will be loaded into this static RAM while waiting for the first stage to initialize the main memory, into which we will be able to load the second stage bootloader. And the second stage obviously will initialize more hardware, all the storage devices, and look up for the operating system kernel on those devices. And once the kernel kicks in, the rest is basically identical to what's done on other devices. So here's a quick comparison. This is just meant, it's really simplified, of course, but it's just meant to emphasize the difference in what the bootloaders need to achieve on different platforms. You can say that the BIOS and UEFI firmware have much more work to do than the boot ROM on the ARM devices, and everything that the boot ROM doesn't do will therefore be executed by the bootloader itself. So it's really much more work for the bootloader, and it complicates a bit the things for us distributions on mobile devices. The main issues is that each system on chip family has its own boot process. First and foremost, the boot order is different, meaning that depending on the storage devices hooked up to the processor. Some processor will prioritize the eMMC, others will prioritize SPI flash, and others will boot first and foremost from an SD card or a non-flash or whatever. So we have to deal with these differences in boot order, and the bootloader location is also different because on the storage device, the first sectors are always reserved for the partition table. So the bootloader cannot be placed at the very beginning of the storage device. You need to then define an offset, and every processor defines a different offset. Some expect the bootloader to be located 8 kilobytes after the start of the storage device. Others expect it 16 kilobytes or 32 kilobytes afterwards, and that really makes it difficult. Even more so because the bootloader needs extensive knowledge of the device and the hardware. It will be responsible for initializing the main memory, so it needs to know which memory it is and the init sequence and all the hardware registers from the processor in order to do so. And it's also in direct control of the hardware. On x86, the hardware is basically accessed by functions provided by the UEFI firmware, for example, whereas on ARM processor, the bootloader has direct access to all the registers and need to handle all the hardware by itself. So that basically requires the bootloader to be adapted to each device, and we need one binary for each device who we want to support. That means also that each device needs to have its own system image, and we cannot easily generate one image which would run on different devices in the same way we could do with 86 computer. Our implementation in the mobile Linux community is to use U-boot in general, which is pretty much the reference bootloaders for embedded systems. It has the advantage of supporting a lot of different architectures, processors, and boards. And it includes also a huge number of device drivers, including, of course, storage devices, because that's where the kernel will be located. The thing with U-boot is that it's meant for industrial devices, and so upstream has a number of defaults which doesn't quite fit with the mobile device use case. For example, they have a 3 seconds boot delay by default, and they expect the vendor for each port to customize it if they need to have a quicker boot process. It's also able to light some LEDs on boot, but you can do more advanced feedback such as LED blinking or changing the color after loading the kernel and stuff like that. And finally, the main user interface for U-boot is the serial console, which is amazing for us developers because we are all used to it and basically have the adapters and hardware necessary for that. But our users, which are not as technically inclined as ourselves, don't have such abilities, and that could be a problem in several cases. In order to improve on that, the Linux mobile community as a whole have settled on using Toeboot, which is not a fork, but rather a U-boot distribution addressing our users' needs. It provides advanced feedback using the integrated vibrator or LEDs, depending on the device, and a simple user interface with an on-screen menu, if it's possible. And most interestingly, it uses the hardware buttons we find on mobile devices, which are generally the volume up and down buttons. They're used to select the boot device or the boot mode. For example, if you press the volume down button while booting, Toeboot will automatically switch to USB mass storage mode, so you can access the internal storage of your device and flash an image directly on it. It uses the distro boot feature of U-boot and also provides a UEFI interface. So we don't have to worry about the specific and just have to provide either the boot script or a UEFI bootloader on the image, or even a configuration file from the X-Linux file format, which is great for us because we really don't need to deal with all the specifics and internals of U-boot at that point. And what makes it even more interesting is that Toeboot is meant to be installed to a dedicated storage device, such as a SPI flash, or dedicated storage area, such as the boot partitions on an eMMC chip. What it allows in practice is that we can distribute images without any bootloader on it. And that's a major step for us to provide a single image to rule them all and to be able to boot on all devices. The next big topic with mobile things is hardware support and device drivers. We want mainline kernel support as much as possible, and the system on chips used in current mobile devices are quite well supported. Just remember that I'm talking about Linux first devices here. And so the processor we use are the Allwinner A64, the NXP IMX8M, and the Rockchip RK3399, with hopefully a few more in the future. But the good thing is that those chips are really well supported by mainline kernel. It's a bit more in work in progress for the NXP1, but things are improving quickly, and thanks to NXP's involvement in this, we're seeing quick progress and really good support for this chip. However, the problem with our devices is that it requires a great number of downstream patches for the device to actually work as expected. At that point, you can probably boot the Pine4 or the Librem 5 from pure mainline kernel, but lots of hardware features won't be handled properly, or maybe it won't work at all. The patches we carry downstream always affect the display subsystem. The cameras as well need a few more patches because it's quite a work in progress area in the Linux world. And we also need drivers for the Wi-Fi chip, the USB-C port, and stuff like that. Hopefully, we'll be reducing this number over time. For the Librem 5, for example, Purism is handling the upstreaming themselves, so we can expect progress on this side. But that's still an important number of patches to carry downstream. This can be explained because some interfaces are specific to embedded systems, or there's a different approach. For example, the displays are connected through the DSI bus, cameras are connected through CSI, which is very different than what we have in x86 computers. In the same fashion, power management is achieved through a dedicated discrete chip, the power management IC, while we have ICPI in the x86 world. So that complicates the work a bit more. And of course, that means we need more specific drivers than computers. For example, on the display side, we need to have a device driver for the display panel itself. Whereas on a laptop, you can have probably an embedded display port connection, and then all information about the display is directly transferred to the display processor. Similarly, for the cameras, we need a driver for the controller, the CSI controller, the sensor itself, because we have raw access to the sensor, and the image signal processor, if any. On laptops, for example, cameras are connected through an internal USB bus So things are much easier on that side, and we don't require any specific driver. How to improve things a bit? Well, first, we can implement new features for existing drivers. For example, proximity sensors have in the kernel an interface, which is the proximity near level interface. This makes user space work much easier because the user space can access this property, and it will tell it at which value corresponds to an object near the proximity sensor. If we don't have this interface, which is the case of the majority of the proximity sensor drivers in the kernel currently, we need to set a specific environment variable for the user space to be able to pick up the proper value and act accordingly. So implementing very small changes such as this one is really helpful to mobile devices. We can also add new interfaces. For example, a few months ago, the chassis type device tree property has been accepted in the device tree specification. So that allows the user space to be aware of what kind of device it is. The values accepted for the chassis type property are laptop, server, tablet, handset. You can also have the embedded value, and so you could envision the power management daemon, which will act a certain way on the laptop and act differently on a mobile phone, for example. However, the upstreaming is currently the weak point for us, and we have a lot of talented developers, but they're all volunteers, and hacking a quick kernel driver is one thing, making it ready for upstreaming and taking the time it needs for upstreaming is something completely different. So it would be great to have a bit more help on that. And yeah, we're trying to make progress. We have a bit more cross-distribution collaboration on that field, but we're still far from the ideal point. Now about the system architecture itself and the specific issues we're facing with mobile devices. Well, it's very much like a normal desktop distribution. We use systemd and dbus, although some distributions rely on OpenRC, such as PortMask, for example. We have Mesa and Wayland for the graphics and display support, and use Pulse Audio for audio management, with future plans of switching to Pipewire as it's becoming the standard in the desktop Linux world as well. We have a few optimizations for this single user use case, such as automatic session startup. On Mobian, this is UID 1000. So that's the default user, and the session is automatically started for this user on boot. Of course, we don't prevent anyone from disabling that feature and installing an actual session manager, such as GGM, for example, and be able to log in through this session manager and choose whatever session they want. We also include limited device-specific configuration. The goal is to have upstream software being able to automatically detect the specificities of the device and act accordingly, but we still need, at least for now, to provide boot parameters for the specific device, a few UDEV rules depending on the case. Some of our supported devices also need specific system scripts and services for proper operation. Those are, for example, devices including a Qualcomm modem, such as the Surface Go or the OnePlus 6. And those devices require a specific script to be run at boot for the modem to be available to user space. We have a few specific needs, however, such as power management. We need to suspend to memory as often as possible. The processors we use in those devices are not really energy efficient, and so they consume quite a bit, and the mean autonomy of those devices is 4 to 6 hours of continuous runtime. So suspending to memory really greatly reduces the consumption, and it allows to have running times of 12, 24, or maybe several days. In some cases, the point phone can actually last up to 4 or 5 days in a mild use case. However, suspending causes some issues with a few peripherals. In general, this is the display, the wireless networking, or in some cases, storage devices. This is mostly due to the device drivers, and there are improvements needed in this field as well. Of course, we don't run one single main application, as is usually the case on industrial embedded systems. The users are in full control, as I already said, so they choose what they want to run in terms of graphical environment, background services, or user-facing applications. So that's something that requires us to have a different approach. For example, we can't easily have a read-only root file system because users will want to install application and they need to config. So that involves quite a bit of a different choice compared to the traditional embedded devices. On mobile phones, we even have a few more things, which is obviously a cellular modem, usually connected through USB internally, but on some devices, for example, using Qualcomm chips, it can be part of the system on chip itself. This modem must be able to wake the device through a GPIO, for example, which will trigger an interrupt and wake up the processor while in suspend, so that you actually get a call. But the connection needs to be a bit more reliable than it is right now. On some circumstances, the modem is not resuming properly, or at least the modem USB connection doesn't resume properly. So that causes issues with, for example, you receive a phone call, the modem wakes up the system, and so the processor does not recognize the modem immediately. So you don't get the information that the phone call is incoming, and ultimately the system won't ring and you won't be aware that you're missing a call. And that's really problematic because we want our phones to be reliable, right? So we have a few workarounds for that. Someone even implemented a custom firmware, open source firmware for the modem used in the PinePhone and PinePhone Pro. But we still have a few bugs to iron out, even though now it's quite reliable on a day-to-day basis. We also need a telephony stack, of course, to handle the modem. In the Linux mobile community, we mostly use Modem Manager because it has a quite active maintainer, and we were able to push really interesting contributions for our use case. For example, we implemented quick suspend resume with so somebody from Postmarked OS implemented that. That means that on resume, the modem is not reinitialized and we can get a phone call quite immediately. We also need to implement custom audio routing procedures because obviously when you are receiving a call, we want the ringtone to be output through the speaker. But as soon as you take the call, we want the output to switch to the earpiece speaker. And so we needed to implement a custom daemon, as we couldn't do it in Pulse Audio directly, unfortunately. And we'll need to discuss a bit with the Pipewire maintainers how we could integrate this a bit more into Pipewire in the future, and maybe get rid or really lighten our call audio routing daemon. We also need to embed a few per device configuration files on our images. As I mentioned, there can be UDEV rules, a few system scripts, and so on. So as we're generating one image for each device, we currently drop any configuration files or fragments we need on the image itself. Optionally, but I believe that's the route taken by most mobile Linux distributions, is that we can package the device configuration itself, so we can easily upgrade it, get rid of unneeded config, or update some to make up for changes in upstream software, for example. But that's a problem, because that ties us some more to per device image files. So why couldn't we store all the files we need for all the devices we support and use only those needed? We could identify the device we run on through the device tree compatible string or the DMI interface on x86, and then read the list of files and fragments we need from the device database we would maintain, obviously. And once it's done, we can generate or copy or link the relevant files to the appropriate location. This is the goal of a project I'm currently developing. It's an early prototype for now and called Trickster. And basically the goal is that on boot, it fully configures the device. Over time, it will even be able to change the configuration if the device changes, so you could use the very same SD card on multiple devices. And that would allow us, obviously, to ship one image for all devices we support, which is ultimately the goal, at least in the Mobian project. Now, finally, the Android devices. As you know, Android devices are quite different because they are not meant to run a normal Linux OS. And also they use processors from two major vendors, which are basically MediaTek, which has very poor mainline support and little to no information is available for those chips, or Qualcomm, which has poor mainline support in general, but some of those chips are really well supported by upstream kernel. That are the Snapdragon 410 and 845, on which Linaro and the community have done an extremely good job at upstreaming support. Android devices also have a very specific boot process because the Android bootloader expects a very specific image format, including in one binary image, the kernel device tree binary file, of course, and the initial RAM disk. So it doesn't look up for the kernel on the file system itself, but rather relies on those images. That means that we need a specific boot image for each device we support, due to the device tree being hard-coded. And of course, every time we upgrade the kernel, we need to regenerate the initial RAM disk and the boot image itself. So that's quite a tedious process, and that's a bit more hassle for us. Android devices being based on the Linux kernel, they can obviously run a real Linux too, once we dealt with a specific boot process. We can't use vendor kernels due to long-term support. They're generally based on old LTS versions and are not maintained for much time. They are deprecated quite early, actually, and they include too many downstream patches to be easily maintainable by a volunteer community. That makes it near impossible to upgrade to recent kernel versions, or even more to track mainline kernel. So there are community efforts for mainlining Qualcomm chips, and that's mostly the case of the post-market OS community, which has a great community of kernel hackers working on many different Qualcomm chips. And that allows us to run actually mobile Linux distributions on quite decent mobile phones, such as, for example, the OnePlus 6, the Pocophone F1, and hopefully in the near future, we'll also be able to distribute images for the Fairphone 4, which is a last generation device with 5G enabled and so on. And that would be great to have that. Because basically, once you have decent kernel support, user space just works, right? We don't have a lot of device-specific configuration as with other phones or tablets. So once we have the hardware support, the user space can just pick up, and we have all the usual interfaces and software running just fine on Android devices as well. Also noteworthy is that the community port of Toeboot is currently being worked on, at least for the SDM845 chip. That will probably allow us in the future to just flash Toeboot in the boot image. So the Android bootloader will chain load Toeboot, which will itself look for the kernel on the storage device and just have a standard boot process as we have for Linux first devices currently. There is still one major problem with Android devices, is that at least on Qualcomm devices, we need proprietary binary blobs to make basically everything work. The GPU, the Wi-Fi chip, the modem, even the sensor and video decoder, IP. And distributing those is a problem because we don't have a clear license to do so. Those firmware are usually extracted from running devices or from OTA images provided by the phone vendor. And that causes a few legal issues. So the solution to that would be to extract firmware at boot time, because the device ships with an actually working Android system, and this system has all the firmware we need on the vendor partitions. So we don't overwrite those partitions for installing mobile Linux. And we could envision that on boot, we would be able to mount those partitions, look for the firmware we need, because thankfully the storage devices don't need any firmware. And we could then put them into the /lib/firmware folder, regenerate obviously the initramfs, and then reboot with those firmware files available to the Linux kernel. And we would then not need any device-specific file, so we could ship a root file system, which would be the same as the one we could distribute with other devices. And that means obviously that extracting the firmware at boot time could be handled by Twixtor as well, and that's actually on the roadmap. So in conclusion, mobile devices are pretty much halfway between personal computers and industrial embedded systems. It allows us to take advantage of the best of both worlds, but we also get the worst of both worlds. That means we able, which is not a really great privilege, but we're able to uncover some hidden bugs due to a different usage. The regular suspend resume cycles is one good example when we can uncover power management problems in existing device drivers. But we also need new solutions to both existing and new problems, audio routing being part of those, obviously. Thankfully, the mobile Linux community is very dynamic and welcoming, and there's a great collaboration across projects. So we can move forward together, and hopefully in a couple of years from now, Most of the problems I talked about today would be just remnants of the past, and we will be in a much better state than now. Here are a few links to the projects I mentioned in this presentation. Feel free to have a look at those. They're all very interesting, and Apertis, for example, is a great embedded distribution. Mobian and Postmarked OS, of course, are really nice projects in the mobile Linux space, and you'll find Toeboot, and even Twixtor is available on GitLab. Thank you for watching, and yeah, feel free to ask any question you might have. I see there are already a few ones in the chat. So, first question, is Linux mobile device privacy and security based like Graphene OS and so on? No, it's definitely not, and we rely on the same security mechanisms are desktop distributions. So you can manually enable things like AppArmor, for example, and use containerized applications using Flatpak or any other mechanism, similar mechanism, but we don't provide any additional security measures than what, for example, Debian already does by default. Next question is, what is the baseline as Linux kernel? Is it an LTS, and do we send back those downstream patches upstream? So we track, we have two versions of kernel available, at least in Mobian. In the stable repository, we provide the latest LTS version, which is 5.15 at the moment. And we plan to track the next LTS as soon as it's available. So sometime early next year, we will upgrade our base kernel. And in the staging repo, we track the latest release of the kernel. So currently we're on the 5.17 branch, and we will switch in the coming weeks to 5.18. And of course, as I mentioned, we would like very much to send downstream patches upstream, but we're having a hard time doing so, and that's a wishful thinking for now, even. But it's taking time, and we're not there yet. But obviously, that's the main room for improvement in terms of hardware support on our devices. So if there aren't any more questions, I thank you all for watching this presentation, and see you soon. Goodbye.